Hey everybody, welcome to my AP Calculus Unit 3 review. Today we're going to be talking about composite, implicit, and inverse functions in terms of differentiation. So let's get started. First, I want to talk about the chain rule. I put here that it's a review because we've already discussed the chain rule. But let me, we did that in the second episode, part 1 of that. So let's just review. So the chain rule, we have here, basically it says that the derivative of a composition of functions, and that's where the composite part comes from, so the derivative, right, this is our derivative operator, of f of g of x, and sometimes this is written using a little o in between, but I don't really think AP does that, so we're just going to stick to it like this, f of g of x, that's what that means. This is equal to f prime, oh wait, hold on, let me make that prime, there we go, f prime of g of x times g prime of x, and that's what this means, okay? So f prime of g of x times g prime of x. So let's look at an example briefly here. So let me put g here, let's say, I don't know, sine of x squared. This is our function, and we want to take its derivative, so let me put the derivative operator there. A derivative of sine of x squared, we're going to take, so basically a way you can really easily think about it is you take the derivative of the outside function, in this case that's just sine, and you keep the inside the exact way it is, because you have g of x in here, you still have g of x in there. So sine, the derivative of sine, is cosine. Okay, and then again, you just keep x squared, you just copy paste it from here to there, right? And then you take the derivative of the inside, g prime of x, which would be 2x, okay? So, this is, and you can put a multiplication there for emphasis. Sometimes people prefer to put like things like this in front of the function so that it doesn't look like it's not confusing or anything. So this is another way to write it. You know, because multiplication, you can flip the order and all that. But this is the derivative of sine of x squared. Something more complicated. Let me think. We can do derivative. You can think of the natural log of. We can do a composition of multiple functions. We can do the natural log of e to the 2x plus x squared. Right? We can just do it like that. So we have our outer function, and then we have our inner function. And part of our inner function has this outer function e to the 2x, which is another inner function. So this is a little more higher level, but we can definitely do this. This is just, okay, so the derivative of the natural log is just 1 over whatever we have here. So this is going to be 1 over e to the 2x plus x squared. Alright, and then now we have to take the derivative of the inside. Derivative of e to the 2x, again, this is a composition of functions. It's not just e to the x, it's e to the 2x. Even though 2 is just a 2, it doesn't really make much of a difference, but it's still another function. It's a composition of functions. So, derivative of e to anything is e to anything. It's the derivative of itself. So we have e to the 2x. But now, this was our outer function, now we have to take the derivative of the inner function. The inner function here is 2x, okay? So derivative of 2x is just 2. So times 2. And then plus the derivative of x squared, this is just regular old x squared, which is just 2x. That's what the derivative of x squared is. And so this is it. And you could definitely, if you want, put this up top. You can do some simplification. Actually, I don't really think there is much simplification you can do. I don't see any. So basically, you could just put this on the top of the fraction, and that's completely okay. So that's the chain rule. Okay, so that's a quick review. So now let's switch gears to implicit differentiation. We can do. I'll just draw a line through there. Now we have implicit. Okay, so let me actually talk about implicit functions first. Okay, so what are the normal functions that we deal with? Well, typically you see something like f of x equals, I don't know, x squared, right? This is a function of x. Sometimes you write this as y equals x squared. This is assuming that y is a function of x, okay? But maybe y is not a function of x. Maybe y and x are both inputs into another function. And we don't really care about that other function, we're just thinking of y and x as inputs. For example, if you have the equation of a circle, okay, that is a very bad circle, hold on. The equation of a circle, that is an implicit function, and I'll show you why. Oh my god, it just keeps getting worse. There we go, that's a little better. Looks more like a potato, but it's okay. So this is a circle, kind of. Let's say the radius is 1. Let's just say, we put r equals 1. The equation of the circle is x squared plus y squared equals 1. This is what we call an implicit function. We can turn it into a function where it's y equals something, but then that would kind of be problematic because that, then it's a function, it has to pass the vertical line test, and then we'd have to choose whether we want the top half or the bottom half. This way, it doesn't matter because it's not necessarily a function, it's just an implicit function. Implicit just means like it's not like defined by this type of thing, it's just two things kind of coexisting, two inputs kind of coexisting and forming this. So this is an implicit function. And in this case, y is not necessarily a function of x. So we can't rely on the standard calculus to, like x squared, we can just easily take the derivative of that. But y squared, how do we do that? So let's talk about implicit differentiation in a second. But first, I want to say that whenever you take the derivative, let's say we want to take the derivative of, I don't know, e to the x. This, we all know, is just e to the x. And then we never write this, but then we have this dx over dx. We could write this, but there's no point because this just cancels out. So why is this there? Why did I just come up with this? Well, if you think about it, this is e to the x times the derivative of x with respect to x. The derivative of x with respect to itself, that's just 1. It just cancels out. You can see that here, that it's going to cancel out. And yeah, technically, you should not put it, but it's kind of there in the background. That's anytime you take a derivative. So what if we take the derivative of e to the y? So let's do dx of e to the y. Well, this is going to just be e to the y, but we're taking the derivative of y, right? We're taking the derivative of y, but with respect to x. That's what that means here, with respect to x. So we can use these facts to help us figure this out. So what we do is we take the derivative of both sides. And you're like, but why both sides? Don't we just normally take the derivative of one? Well, not really, because here, this is just an expression. We have this expression here, and we're taking the derivative of that using our operator. Usually we have something like f of x, I'll erase this in a second, but f of x equals natural log of x, okay? And then when we take the derivative of both sides, let me actually make some room here for that, ln x. So we take the derivative of this side, and then we take the derivative of this side, right? So then the derivative of f of x is just f prime of x. And the derivative of natural log of x is just 1 over x. So this way we're taking the derivative of both sides, so don't be like so weirded out by that, like why are we taking from both sides? Yeah, we're just doing both sides here, okay? So let's take the derivative of x squared plus y squared equals 1. And it's really hard to write this, so let me just do it this way. So x squared plus y squared equals 1. Let me make that squared a little better. And then we're going to take the derivative. So again, this is what I'm saying. It's kind of hard to write. I like to kind of like draw like an arrow and just say d over dx, just to know that I'm taking the derivative with respect to x. So this turns into 2x. And again, we could write the dx over dx, but there's no point. This is just x squared. We know how to take that derivative. Plus, now it's y squared, which is 2y. But remember, we have this dy over dx. And you could also write y prime. That's another way you could write it. It's just up to you. Sometimes it's kind of confusing if it's 2y, y prime, then it's weird. So I would recommend writing it this way, but it's up to you. And this is equal to, well, 1 is just a constant that when you take the derivative of that, it just goes away. So now, what our job is to do is to isolate dy dx. Because that is saying, because if we have dy dx equal to something, let's say the derivative of y with respect to x is equal to this. That's what we want. So let's do this. So 2y dy dx equals negative 2x. We just move this to the other side, and then we can actually just cancel out these 2's just because they're both there. So then we have y dy dx equals negative x, and then we just get that dy dx equals negative x over y. And if you want to find the tangent line, I actually never mentioned this, but you can find the tangent line of a derivative. That's probably going to show up on the AP exam. Tangent line, you know that it's just y minus y1 equals the slope times x minus x1. That's for a tangent. For a normal line, you just take the opposite reciprocal and you're going to get negative 1 over m. Basically the opposite of your slope. And so if they give you a point, you can plug these in, and then basically that'll give you the slope, and then you can plug that into your equation there, basically using everything else, because you'll have your y1 and your x1 based on that point. But yeah, so if you need more practice on tangent lines and stuff, you can definitely find some videos on YouTube about that. That's more of a kind of algebra concept, but applied to calculus, so I'm not going to go over that too much in depth, but this is kind of what you're going to use. Okay, so we've covered implicit differentiation, of course implicit functions, chain rule. All we got to do is find inverse functions, and also we're going to do some higher order derivatives, and I'll tell you what all that means in just a second. Alright, so now we're going to continue. I kind of lied when I was telling you what I just said. Basically, we're going to do inverse functions and logarithmic differentiation. I'll go through that in a second. But basically, we already went through the inverse trig functions in the last video, AP Calculus Unit 2, Part 2. So be sure to check that one out. I went through that briefly in the last few minutes of the video. But basically, we're going to be talking about inverse functions in general now. So if you want to take the derivative, let's do it this way. So the derivative of f inverse of x. And this is kind of weird because it's like, well, how do we do that? Well, by using implicit differentiation, you can do it in a very cool way. You could say, well, y equals f inverse of x, right? Right? This is, so we can set y equal to f inverse of x. Now we just take the derivative of both sides, right? Oh, well, actually, I mean, we could, but like that won't get us anywhere. First, what we want to do is we want to take f on both sides, like compose, like we'll have f of y equals f of f inverse of x. Well, f of f inverse of x is just x itself, right? So we'll have f of y equals x. And, you know, after we take f on both sides. Okay. Now if we take the derivative on both sides, so let me draw my arrow, dx. Okay, so we get f prime of y dy dx, right, because we can't remember dy dx. This is just equal to 1, right? So that's really cool. So now we can isolate dy dx by dividing the f prime of y on both sides. We get 1 over f prime of y. We're not necessarily done here because we didn't have a y in the original problem. We just had an x. We just created this y. So we can't keep the y. We have to have something in terms of x. Well, we said that y was just f inverse of x, right? So we can just substitute that back in. because all we did was make a substitution. So we get that this is equal to 1 over f prime, right? Because we have this f prime here of f inverse of x. And that is the derivative of f inverse of x. It's equal to this expression. Now, what if we had, what if we wanted to evaluate this at, I don't know, x equals a, right? And so x equals a, basically. So first, before I do that, let's think about this. So if we have, let's say, f of a, hold on. Okay, so if we had capital A, and it's not the same as lowercase a, it's different. So if this is equal to f inverse of lowercase a, then we have that f of capital A equals a, right? Because if we take f on both sides, it's going to cancel out. So f of capital A equals a. So really, we're just saying that this is just x equals f of capital A. And I'll show you why that's useful in a second. But basically, we could just say this. Because if we plugged in a here, it's not going to really help us much. But if we have f of capital A, that really helps us a lot. Because now we can say, well, okay, dy dx. And again, it's okay to have the y here. Technically you should have f inverse of x, but it's acceptable. They know what you're talking about. So this is going to be 1 over f prime of f inverse, hold on, of f inverse, f inverse of f of capital A. So f inverse and f cancel out, so this is just equal to 1 over f prime of capital A. That's really cool. Because basically, if you know that f inverse of a is equal to capital A, then you know that f of capital A equals a. Alternatively, let's say you didn't know this. You only knew that f of capital A equals lowercase a. Well, you can say, well, I know that if I take the inverse on both sides, I'll get that a is just equal to f inverse of lowercase a. Just like that. So that's a cool little thing you can do to figure out inverse functions. We talked about the inverse of the trig functions. Natural log and e to the x are inverses of each other, so we talked about that. Now let's talk about logarithmic differentiation. So let me just draw a line through here. We're going to talk about logarithmic differentiation, which is a cool application of implicit differentiation. So let's say we have y equals x to the x. We don't know any rules for this. We can't do like the power rule where it's like we bring this to the front and subtract 1. No. We can't do that. That's only if you have like a number up there. Here we can take the natural log of both sides and then be able to take the derivative. So you know how we like took the f of both sides? This is kind of the same thing. So this is pretty similar. We're going to take the natural log of both sides. So if we do that, we get ln y equals ln of x to the x. Does this help us? Well, yeah, this side, the x goes to the front. Not derivative, just the regular logarithm rule where you can bring the exponent to the front. So we say that ln y equals x times ln x. And then from here, we can see that, okay, well, we can take the derivative on both sides. So let me draw a little derivative sign. We can say that this is 1 over y, but times dy dx. Always remember your dy dx because we're going to isolate this. And this is equal to, well, we just use the product rule on this side. So we get that this is x times 1 over x plus ln x times 1. That's just the product rule. So we get that dy dx. And we have to we isolated this by multiplying y on both sides. So we get that this is y times x times 1 over x is just 1 plus ln x. But again, we can't just keep y because we introduced y here. Technically, it wasn't here. We just had like a ddx, right? and then what we did is we just made y equal to x to the x. That's like an artificial thing we did. But you know, so we have y here. Y is just x to the x, so we can get our solution. So this is equal to x to the x times 1 plus ln x. And this is your solution. And you can think of other functions to do this with. This is logarithmic differentiation. I have a whole playlist on this on my YouTube channel, so if you want to check that out, you're more than welcome to. I'll leave a link in the description below. But yeah, this is what logarithmic differentiation is. And now let's talk about the higher order derivatives, alright? Alright, so now we're going to talk about higher order derivatives. It's really not that hard. So if we have f of x equal to x cubed, its first derivative, like we're used to, is just 3x squared, right? But what's this? This is our second derivative because we have two apostrophes. And that's an apostrophe, not a 1. I write my primes a little weird. But you know, so this is our second derivative, which is going to be, well, we move this to the front, so we get 6x. And our third derivative is going to be 6. So what is our fourth derivative going to be? So 1, 2, 3, 4 of x, this is actually just equal to 0. And then if we take any other derivatives of this, we're going to get 0. So that's pretty cool. But how else can we do things like this? Well, this is actually pretty cool because it leads us to something that's very interesting. Actually, before that, the derivative of e to the x is just e to the x. So any number of derivatives of e to the x alone is just going to be e to the x. So that's pretty cool. Now, what I really wanted to show you is how sine x works. So if we take f of x equal to sine x, then we get f, and let me use another notation here. So if we have in parentheses like a 1, this is a 1, these are primes, I'm going to put numbers here, and this just means the first derivative. So this is equal to, well, this is just cosine x, right? And then if we have f of to the 2 power, not f to the 2 power, it's f, the second derivative of f, and this is equal to, well, what's the derivative of cosine? Negative sine, right? So negative sine of x. Okay, so then the third derivative equals, well, derivative of sine is cosine, so the derivative of negative sine is negative cosine. And then the fourth derivative, okay, so the derivative of cosine is negative sine, so the derivative of negative cosine is negative sine, which is sine of x. So sine of x. And this is our original function. So if we take the fifth derivative, it's just that. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on and so forth. So this is pretty cool. So if you have any multiple of these numbers starting here, or it'd be like 4, so if we have like 3 times 4, or 3 plus a multiple of 4, then you'll know that that's what it is. So that's a little pretty cool side note. I just thought that was worth noting. You know, higher order derivatives, they're not very hard to think about. And in the next video, whenever we talk about the applications of derivatives, you'll when we talk about motion, you'll see how these derivatives come into play. Alright, so that's pretty much all I have for you today. I hope you enjoyed. Thank you so much for watching, and I'll see you in the next video. Bye, guys.